In this lesson, we're going to talk about probability, which some of you may be familiar with and some of you may not have heard of before. So we're going to start by doing a number of definitions to help us get a better sense of what we are studying. And then through this lesson, we'll end up talking about how to calculate basic probability, looking at the difference between theoretical and experimental probability. Okay, so let's go ahead and get started. The first thing we want to define is what's called a probability experiment. And a probability experiment is an action or trial that has varying results. So I think it's basically a fancy way of saying you're doing something that will give you different results. Like you're rolling a dice and you have 6 different results, right? You can get 1, 2, 3, 4, 5, or 6, a standard dice. Or you flip a coin and you have 2 results, heads or tails. So that is what we call a probability experiment. It doesn't have to be something crazy that you might think in science that involves a lot of different variables and techniques. It could be as simple as flipping a coin. Okay? So what is an outcome? The outcome is basically the possible results of a probability experiment. Okay, so if we go back to what I mentioned at the very beginning when I talked about different probability experiments, like rolling a standard dice, 1 through 6, then your outcomes are literally the numbers 1, 2, 3, 4, 5, or 6, right? If you flip a coin, your outcomes are heads or tails. So it's just what you could get out of it. That's the outcome, okay? What is the event? The event is a collection of one or more outcomes. So basically an event is kind of a fancy way of saying, you know, this or these 2 things will happen. So it's kind of what could possibly occur. All right. And then finally, what is a sample space, which is going to be that first example we're going to look at. A sample space is a set of all possible outcomes. So often we can use different visuals to demonstrate the sample space, like a list or a tree diagram or a table. So in example 1, we're going to flip a coin and roll a 6-sided dice, a standard 6-sided dice, not biased, fair dice. How many possible outcomes are there in the sample space? List the possible outcomes. So what we want to do is actually depict what could happen, right? You can make a list, you can make a table, you can make a tree diagram. Those are the most popular ways to make a sample, to draw out a sample space. And each of those will definitely give you all the possible outcomes. Okay, so let me show you a tree diagram first. So this is my tree diagram. What you would do is you have 2 different things happening, right? You're flipping a coin and you're rolling a 6-sided dice. So you'll start with the outcomes of one of those situations. So I'm going to start with my coin. My possible outcomes are either heads or tails, right? But after we flipped our coin, we're also going to roll the dice. So afterwards, we're going to go ahead and roll our dice. And what are the outcomes of the dice? Well, we can roll a 1, 2, 3, 4, 5, or 6. And we can roll a 1, 2, 3, 4, 5, or 6 after we flip a heads. But we can also roll a 1, 2, 3, 4, 5, or 6 after you flip a tails. So this tree diagram has 2 starting points. Either you flipped heads or you flipped tails. And connecting to either heads or tails, you have 6 possible outcomes from the dice, which gives us this list of possible outcomes. You can have heads and a 1, heads and a 2, heads and a 3, heads 4, heads 5, heads 6. Also tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. So we have a total of 12 outcomes. So one thing you'll realize is to figure out how many possible outcomes there are, you just multiply, right? We have 2 possible outcomes from the coin, 6 possible outcomes from the dice. 2 times 6 is 12. Okay. Another popular way of depicting your sample space is by doing a table. And the table, I should mention, is limited because you can only have 2 events occurring. So either flipping a coin, so you can flip a coin and roll 1 dice, that's 2, right? You can roll 1 dice and then roll another dice, that's 2, but we can't do coin, dice, and then another dice. If you're doing more than 2 things, you would want to do the tree, because the tree will let you expand your branches as big, and you can get as big as you want. You can put on like 5 different things, situations, right? A coin, a dice, another coin, and then 2 more dice, and you just keep adding down. Oops, sorry about that. There's my dog. Okay, but if you're interested in the table, which can be a little bit easier to read, you just basically make a chart, right? So you can decide how you want to set that up, but we have two possibilities or two situations, right? So I'm going to let this side be my dice, or sorry, my coin, because I can fit that in this way. So I either have, again, heads or tails from that coin. And then what are the possible outcomes from your dice? Well, if I let this top kind of row here be the dice, I have 1, 2, 3, 4, 5, and 6 as my possible outcomes. And then you just basically put the two together. I didn't give myself a ton of space there, but you can see here's heads and 1, tails and 1, heads and 2, tails and 2, heads 3, that's an H, and a 3. Let me rewrite that. Heads 3, tails 3, and you get the idea. And that gives you all 12 outcomes that we got from the tree diagram as well. So again, good and bad to both. Tree diagram, if you have a lot going on, it can definitely get confusing to read because you just follow the lines, right? You go heads to 1, heads to 2, tails to 1, tails to 2, etc. But it's great because you can have more than 2 events occurring at the same time. And then here with the table, I think it's a little easier to read, but it's limited because we can only do 2. All right, but regardless, how do we get the total number of outcomes? You just multiply, right? 2 times 6 here gives us 12. Cool. So now that we know how to find a sample space and we know what the all possible outcomes are, now we actually want to talk about probability. Because what is probability? Probability is the likelihood of a certain outcome or outcomes occurring. So again, a measure of the likelihood or chance that the event will occur. So you probably heard probability, that word at least, being used. So, right, you might see on the weather portion of the news, they say the probability of rain tomorrow is, 60% or 0.6. So that's telling you how likely things will occur. So if you look at the graphic underneath that vocabulary, you'll see probability is always going to go from 0 to 1 in terms of decimal values, or in their corresponding percent format, 0% to 100%, where 0 is it's definitely not happening, it's impossible, to 100% or 1 being yes, it is definitely happening, and everything in between is just telling us is it likely or unlikely. So the closer we are to 0, it's more unlikely. The closer we are to 1, the stronger it is, more likely it's going to happen. And if we're right in the middle, 50-50, it is equally likely to happen or not. So you get to hear that a lot, right? The 50-50% chance, and you're like, well, it's kind of up in the air. Okay. So when we talk about calculating probabilities, we have 2 types of probability, theoretical probability and experimental probability. So we're going to look at how to calculate theoretical probability first, but let me just give you a little information about what is theoretical probability. So theoretical probability is in theory, right? So it's not actually something we observed, like you're actually looking at, 3 kids out of 50 are wearing glasses. So it's unlikely kids I'm going to randomly select a kid who wears glasses or something like that, right? You're not observing anything. You're basically using the sample space, which are all of your possible outcomes, to generate probability. Okay, so how do we calculate this? Well, usually we like to use a capital P to represent probability, and then in this parentheses, we put in A or whatever outcome we want. So this is what we call a favorable outcome. Or again, the event that we want to happen. And this is a really, really simple calculation. You just basically make a fraction. It's the number of favorable outcomes in that sample space over the total number of outcomes. So a very simple example is if you're looking at just flipping a coin, you have 2 possible outcomes, heads or tails, right? So our denominator there would be 2 because we have total of 2 number of outcomes. If I want to do the probability of heads, that's my favorable outcome. I have 1 head out of 2 outcomes, it's 1/2. So very simple fraction creates the decimal, right? And then, or the fraction, which we can create a decimal out of, and then we can make a percent out of that to give us one of the 3 forms of probability. Again, a fraction, decimal, or percentage. And they're all going to be telling you the same thing. Okay, so let's take a look at example 2, where we can use a sample space to help us calculate the probability. So in this example, a student is taking a quiz and they randomly guess answers to 4 true-false questions. What is the probability that the student will guess exactly 2 correct answers? So what you'll want to do here is think about how would you list out all the possible outcomes? Because we do need to know how many different combinations of guessing the 4 true-false questions would be. And here's where the sample space can be a little tedious, but you do want to stop and think, wait, how am I going to actually draw it out? And in this case, because we have 4 questions, I think the best thing to do is actually to do a tree. So I'm going to go ahead and start with question 1. So for question 1, you have 2 possibilities, right? I'm going to use C for correct and I for incorrect. You can either, oops, sorry about that, get it correct or get it incorrect. Oh, my goodness. Sorry, moving things around. So question 1 can either be correct or incorrect, right? So I could guess right, guess wrong. Then question 2, we have the same situation, right? I could have guessed the first one right and the second one right as well, 2 in a row, or I could have gotten my first incorrect answer from there. Alternatively, if I guessed the first one wrong, I could still guess the second one right, or go on a streak here and get 2 wrong in a row. And then I just keep layering on. So question 3, same deal. I could either guess correct, and kept going on that lucky streak, got a 3rd one correct, or get my first incorrect. So you can see how each of these are going to branch off into, again, 2 possible outcomes, but we're layering it so we can have correct, incorrect, and so on. So you can see how the tree kind of expands as we add more layers onto it. And each of these branches becomes a path. So we'll follow the path. Starting with C, we can go C, 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 or C, C, I, C, I, C, etc. And that leads us to the possible outcomes. So one outcome from what I'm seeing right now could be 3 C's in a row, 2 C's, and then an I, right? So I'm just following the paths. I'm going to add one more question on here because we have 4 questions. And again, underneath each of these CIs, I'm going to add in another correct or incorrect. So that's how the tree diagram works. And while I just finish writing all this down, and oh, I've written everything kind of squished together. So let me maybe clean this up a bit. But you can listen to me talk while I'm doing that. I should mention you don't always have to have the same outcomes in your tree diagram. So you see how all of these are correct or incorrect? That's because we're looking at the same situation, right? For the same types of questions, or 4 questions in general on an exam or a quiz. But you could do, like we saw earlier, the heads and then the dice. You could do, right, wearing a sweater and then suddenly switching to wearing green socks. You just write the different types of outcomes underneath. And it doesn't always have to be 2. It could be 3, it could be 5. It depends on the situation. So that's kind of the power of the tree diagram. But again, you can see how it can get tedious and kind of long as you add more to it. Okay, so let's get back to the problem. So remember, we want to guess exactly 2 correct answers. So how do we do that? Well, remember, theoretical probability, this is what we're doing here, is we're not actually saying, okay, how many did he guess correctly and look at over time what his probability is, but we're saying, okay, what are the chances he could guess 2 correctly? So the probability of 2 correct answers is going to be the number of outcomes with 2 correct, right, over the total number of outcomes. How do we know the total number of outcomes? Again, you can multiply, right? I take that back. We can't multiply here because we're looking at not a situation of 2 events, but we're looking at 4 all linked together. So what we want to do is we basically just want to count at the bottom, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, right? Because each of these paths ends here at a C and an I, C and I at question 4. So we have a total of 16 outcomes. So that means my probability is going to have a denominator of 16. Now, how many of these branches lead us to exactly 2 corrects? That's what we need to count now. So if you want, you can list out all the different combinations. So starting with the first C, we can go C, 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 then C, 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 I, C, C, I, C, and you can write them all out if you'd like, if it helps you visualize it. I'm just going to kind of trace out my branches and see where I get exactly 2 C's and 2 I's. So if I start here at the beginning, the first correction, let's say I guessed correct, I can guess the first one correct, the second question correct, and then I want 2 incorrects after that because I can't have more than 2 C's in this situation. So there's 1, C, C, I. Okay, but I can also look here on my second branch from C. I can guess the first one correct, incorrect, but then I can get another correct here to get 2 C's. It doesn't have to be 2 C's in a row. It just says 2 C's in general. So there's 2. Then look in here, right? C, I, C also gives me 2 corrects. So that's 3. And if I go C, I, that's 1 C and 3 I, so that's not going to work. So I'm just basically checking each branch. So starting now with the incorrect, if I guess the first one incorrect, I could still get 2 correct by going I, C, C, I don't want the third C, right? I can go I, C, that's still 2 C's. I can't go I, C, I, that's not going to work. I can also go I, C. And the rest of these, I, C, I, C, I all have too many incorrects, so that's not going to work. So if I just look at how many of these red paths I highlighted, so remember, these paths connect all of them to create one outcome. C, C, I is one outcome, right? It's not 4 outcomes together, it's 1. C, C, I is 1. C, I is 2. So I can count up those red paths, and I'm going to see I have 6. So my probability is 6 over 16. So as always, good manners, let's simplify our fraction. So that's going to give us 3/8. And if it doesn't specify, I'm okay if you just leave your probability as a simplified fraction. However, probability, like we saw earlier, I'll just scroll back to show you the graphic, it could be given as a fraction, decimal, or percentage. Okay, so here, because I didn't ask you to round, just give it to me as a fraction. It's the easiest thing to do. But if you wanted to round it, you would just go 3 divided by 8. If you want it as a percent, you go 3 divided by 8 times 100. Okay, so that's one way of doing theoretical probability. All of our situations are going to be different depending on the problem. So example 3 is an interesting one that applies a little bit of geometry to our probability. So here in example 3, we're still calculating theoretical probability. What we're doing is we're going to throw a dart at this board, and our dart is equally likely to hit any point inside the square board. Hopefully you guys picked that up. It's a square board. We'll come back to that in a moment. Are we more likely to get 10 points or 0 points? So how do we even know how to calculate this probability? Well, if we're going to land inside the board, what is that called when we land, or when we're just dealing with space inside? We're going to deal with area, guys, right? So we're going to compare the areas. Okay, we want to determine, right, are we more likely to get 10 or 0 using probabilities? So I'm basically going to do 2 different probability calculations. The probability of getting 10 points is going to be looking at, where is the 10-point region? Well, that's right here, right, in this pink area. This is a circle. What's the area formula of a circle? That's what we have to go back and think about, right? But the probability of getting 10 is going to be the area of the smallest circle over, and we're going to land anywhere inside the square board, which is the area of the square. Okay, so remember, area of a circle is pi times radius squared. The radius of that inner circle is 3, right? Based on what we see here, that 3 gives us the radius. So pi times 3 squared over, then how do we figure out the area of a square? Well, area of a square is length times width. All the 4 sides are exactly the same, so we can just do side squared. So if we know that this distance is 369, and it goes to the center of the circle, we know this radius is also 9. So then that side is actually 18. So the area of the square is just 18 times 18. So this will be 9 pi over 324, or pi over 36. Okay? And because I'm going to compare this, and I'm not actually asking you to give the answer, I'm going to go ahead and convert this into a decimal, because for me it's a lot easier to determine what's larger or smaller based on decimal values. So I'm just going to take pi divided by 36, and make sure you use the pi button in your calculator, not 3.14. And let's round this to the nearest hundredth. So I get 0.09. So that gives me kind of a baseline to work with, so I can see, okay, if the probability of getting 0 is, 0.03, then it's definitely more likely that we'll get a 10 than a 0. Right? So that's what we're doing here. So now let's go ahead and find the probability of getting 0 points. So this one's a little bit trickier, because you might think, wait a minute, I know how to find the area of a square. I know how to find the area of a circle. I know how to find an area of a triangle. But what is this business? Because 0 is all this blue space right here. This is kind of a curved triangle. And we don't want to say, well, it looks kind of like a triangle. Why don't we just do 1/2 base times height and work with that? But that's not the true area, because we want to be as accurate as possible. So I want to figure out what's the area of all those purple little corners. Well, if we can't calculate that area, what we can do is find the area of the square itself, find the area of the largest circle, and just subtract. And what's left over would be the 4 corners, right? So I'm going to take the area of the square minus the area of the larger circle, right? Because if I take the area of the square and take away that yellow circle, what's left over is just going to be those corners. And that's how we can get the exact area without worrying about how do we deal with those curves. And again, we're still doing it over the entire dartboard, which is the area of the square. Okay, so we said earlier the area of the square is 18 times 18. The area of the larger circle, so the circle still pi r squared. The radius of that large circle is going to be 369. So this will be pi times 9 squared over, again, 18 times 18. So 324 minus 81 pi over 324. Please don't be tempted to tell me 324 over 324 becomes 1, and this is just 1 over 81 pi, or 1 minus 81 pi. We cannot simplify this. Please don't simplify this. What you're going to do is do this in the calculator. Do 324 minus 81 pi, see what we get there. And again, it's okay to use a decimal because we're just figuring out which one is more likely. So we're not actually worrying about giving the actual exact number today. So I can round that to 69.531 over 324, which is roughly 0.21. And then what I want to use is I want to use these two numbers to tell me, okay, am I more likely to get an awesome score of 10 or kind of hit one of those corners and get 0? And here it's clearly, right, more than double your chance of getting the 0. The 10 is actually getting a 0. So we're more likely to get 0 here. So I'm going to try to, let me just scoot this over and then I will write down my answer, because our answer here should be a sentence explaining the answer. So you are more likely to get it 0 points because 0.21, that probability is higher than the 0.09. So there's my answer right there. Okay. So moving on, we can also talk about the probability of what we call the complement of an event. So let me kind of section this off because I kind of used extra space there. So what is a complement? It's kind of like what I was just doing with the, square minus circle gives me the result, the leftovers. The complement is basically what you look at with the outcome and then, let me think. So it's basically what makes a whole, if that makes sense. So let me just show you. The probability of a complement is 1 minus the probability of the actual event, because the two together make 100%. Right? Kind of like how we were looking at with the square and the circle in that last example, right? If I take the area of the circle, add on the corners that I got from doing the subtraction, I get one whole square. Because if you're going to have like a situation where you either have heads or you can have tails, the two together make 100%. You're going to have either heads or tails. So we use that 1 to represent the 100. And if we take away the probability of an event, we get what's called the complement. And often you'll see the notation for complement is this apostrophe. But you can just say complement. And do you have to find it this way? No, it all depends. Sometimes it's actually easier to do the complement than to actually count the actual probability. So we'll see this with example 4 right now, here up next. Okay, so in this example, we have two 6-sided dice, which you can see in the sample space there on the right. And what's nice is you can also draw like a depiction of your sample space. So we see all 36 outcomes here. Right, one dice in white, one dice in black. We can have a 1-1, a 1-2, a 2-1, a 2-3, right? And we have all 36 outcomes. Because we have two situations, you can also find the total number of outcomes just by doing 6 times 6. So that's a side note there. So if we are trying to find the probability of each event, we can definitely use the sample space. So if you look at A, we want to find the probability that the sum is not 6. Right? So what you can do is you can definitely go to your sample space and start counting how many of these aren't going to add up to 6. So 1 + 1 is 2, that's not 6. 1 + 2 is 3, that's not 6. And I can keep going and count them all up. However, I want to show you why the complement is also kind of nice to work with too, because if I'm counting them all up, there's going to be a lot that aren't going to equal 6, right? But if you think about it, the numbers that add up to 6 and the numbers that don't add up to 6 together create all 36 outcomes because it's one or the other. Right? So together they create 100% of our sample space. So what we can do is we can say, hey, it's going to take me forever to count up the ones that are not 6. Why don't I just do 1 minus the probability that the sum will be 6? Because then I'll just get what's left over, which should be what we call the complement, which would be the probability that it's not 6. Because it has to be either 6 or not 6, right? There's no way it can't be either. Or both, right? So instead, I'm going to go ahead and just look for where is it 6, because I know 6 really easily. It's 1 + 5, it's 2 + 4, 3 + 3, 2 + 4, and again 5 + 1. So those 1, 2, 3, 4, 5 out of 36 are going to add up to 6. So to calculate the sum being not 6, I'm going to do 1 minus 536. And we can just get a common denominator here. So 36 over 36 minus 536 to get us an answer of 3136. Now, would it be wrong if you counted all 31 options? No, you get the same number. But this gives you an option, and you can see how the complement works. So for some people, maybe this is a lot faster than counting up all 31. Or maybe it gives you a way to check, because if you're like, wait, did I get all of them? Let me just quickly calculate the complement, and you can see, okay, it should have been 31 over 36. If I got 30 over 36, I might have missed one. Okay? So if you guys want to try this part B on your own, go for it, and then just hit unpause when you're ready to hear the explanation. But you can, again, count or work with the complement, whatever is easier for you. All right, so again, you could have counted how many combinations would add up to a number that is less than or equal to 9, so 9 all the way down to 2. Or on the other hand, if you want to use the complement like I did, it was a lot faster for me to just count how many are actually over 9, so 10 and above. So I can do 4 and 6, 6 and 4, 5 and 5, right? And just that little corner here on the right. And then I just did 1 minus 6 over 36, 1 minus 1, 6 to get 5, 6. Just remember, if it doesn't say it around or anything, just leave your answer as a simplified fraction. If it does say it around, please do round to the right place value. Okay, last up for this lesson, we're going to deal with what's called experimental probability. So up to now, we've talked about theoretical probability that worked with the sample space. So in theory, we have 36 possible outcomes from rolling these two dice. So what's the difference with experimental probability? Experimental probability actually uses observed results. So rather than saying, hey, we have 36 different possibilities, we're going to roll those dice like 20 times and write down what each of those rolls are. And maybe in those 20 rolls, we don't get some combinations, like we don't get 3 and 5, or we don't get 2 and 2. And that's okay, because what we're going to do is we're going to do their probability based on the outcomes from our trials. Does that make sense? So we're not using the overall sample space that in theory we have 36 different outcomes. We're going to look at just what we actually rolled. And when we calculate probability, it's still the same. It's the number of times we get what we want or what we're looking for over the total number of trials that we've done. So again, those trials are the experiment, I guess the experiment that we're doing. Like we're rolling the dice and we're going to do 20 trials and we have 20 different outcomes. That's what we're using to calculate probability. But the probability calculation, again, the probability of some event we want, A, is our number of successes, which is basically, right, the number of times we get A over the total number of trials. Right? So again, if I'm doing that dice roll situation again, let's say we rolled it 20 times, and out of those 20 times, we got a sum of 2 once, then our experimental probability would be 1 out of 20, rather than the theoretical probability being 1 out of 36. Do you see what I'm saying with the experimental versus theoretical? The denominator is what changes. All right, so if we take a look at the last example, to wrap up this first set of notes on probability, each section of a spinner is shown here, blue, yellow, green, and red, and the spinner was spun 20 times. So the table shows our results of our 20 spins. For which color is the experimental probability equal to the theoretical probability? So what we want to do here is we want to calculate both of these. So what's nice about this is because it told us every area is exactly the same, we have 4 pieces of one whole circle. So my theoretical probability of any color, sorry, my writing is so messy, for any color is going to be 1/4 because each color occupies 1/4 of the circle. So the question here is which one of these experimental probabilities will match that? Remember, you want to communicate your entire work to me. So before you just say, okay, it's red or it's blue, I want you to show me all of the experimental probabilities. So we want to find the experimental probability of landing on red. Well, that's how many times we landed on red, which is 5, over the number of trials. So we did a total of 20 trials. So I'm going to put 20 in the denominator. Oops. And then we can simplify that to 1/4. So we know for sure red definitely matched. And you can probably tell like green, blue, and yellow won't match, but that's why I want you guys to show me all of your work, because we want to show definitively that red is the only one that did match. So the probability of green is 9 out of 20, which doesn't simplify. The probability of blue is 3 out of 20, and the probability of yellow is 3 out of 20. So based on all 4 of these probabilities, we can be super confident that the only one that matched is red. So red is our answer, right? And then our work shows why it's only red and not the rest. So that is our first section on probability. We kind of went through a lot of vocabulary. Hopefully you realize to calculate probability, it's very straightforward. It's just making a ratio, making a fraction, but be very careful with the vocabulary, right? Read the directions very carefully. As always, if you have any questions, please let me know, and thank you for listening.